Well, hello there. Today we are going to go over the advanced math lesson number 3. And I am doing this right now without the book in front of me, so I hope that I do a good job. I do have little pictures of what is in the book, but we'll see. I'm just going to try it, and if it doesn't work out, it's okay, whatever. I'll do it over again. But today's lesson, I really love this lesson. I put a lot of work into it. I hope you really like it. It is about the Pythagorean theorem, which you know already. Remember, you might remember it from like the Lego Batman movie, a squared plus b squared equals c squared. Remember that part of it? We're going to go over that and what it means. We're also going to go over triangle inequalities and then similar polygons and similar triangles. I actually think this is the funnest lesson that we have done so far, so I think you're really going to like it. Don't worry, it's not super confusing. That was my lead into this little joke of the day, this little meme. The teacher is saying, don't worry, the test isn't that confusing, and here's the test. Question 38. What is a microphone? True or false? Okay, I hope that my test questions are not like that. That's not exactly fair. Let's start by going over the Pythagorean theorem. Okay, this hottie is the Greek mathematician whose name was Pythagoras. And he's not around today. He can't be your boyfriend. He lived actually in the 6th century BC. And his theory on a squared plus b squared equals c squared was actually based on geometry, not based on algebra. Algebra wasn't even invented yet. So he came up with this based on just knowing geometry, which is kind of cool. And this is what it means. If we look closely at this, here in the center we have a triangle. So look at this gray triangle. We've got a side with a length of A, another side with a length B, and the longest side, if you remember what that's called, that's the length of the hypotenuse. The hypotenuse is called C. Now, if you take the length of that side and square it, so it's C squared, you literally get a square, an area, right? And you've got this area C. If you do that with A, you've got this area A. And if you do that with B, you've got this area of a square. And if you sort of show with shapes what we're doing mathematically, it's this. The area of A squared and the area of B squared is going to be equal to the area of C squared. Okay, so if you've got like a tablecloth or a piece of paper or something that has an area and you add up this area plus this area, it's going to be exactly the same as C squared. So that's kind of cool. But it only works for right triangles. So I'm going to put a little square right there to indicate that that is a 90-degree angle in this triangle. It has to be a right triangle. So you can remember that by thinking Pythagorean was right, but it only works for right triangles because A squared and B squared have to be the shorter side, C squared has to be the hypotenuse in the right triangle. Okay, what if it's not a right triangle? What if it's actually a triangle inequality? So that's what we're going to go over next. They tell us the first sentence in this part of the book I thought was super confusing. It says the sum of the lengths of any two sides of any triangle is greater than the length of the third side, whatever. Okay, that's hard. So I am going to tell you a story and then you will know that statement inside and out. Okay, so imagine that you are walking in a fairy tale and you are about to cross a bridge and the bridge is guarded by a troll. See, look at this troll right there. You want to get across this bridge, but of course, like trolls do, they want to ask you a riddle and you can't cross the bridge until you know the answer, the solution of the riddle. This troll has 3 bars of gold. And we don't know, he doesn't tell you, because, you know, trolls are kind of iffy this way, the length of the sides. So we don't know how long these lengths are, but maybe he has one long one and maybe he has 2 shorter ones. We don't know, but it could be like that. Now he says to you, you can either have 1 bar of gold or you can have 2 bars of gold, but you have to you have to get the most gold that you can. Would you choose 1 bar or would you choose 2 bars? And he can make a triangle out of these bars of gold. So that's the information you know. That's the riddle. He can make a triangle by arranging the bars of gold. And you have to choose whether you're going to take 1 bar or 2 bars. And you have to get more gold than him. So this is tricky. Like what I want to say is I want to say, well, of course I'm going to take 2 bars instead of 1 bar because obviously 2 bars have more gold than just 1 bar, right? But is there a way that you can have a triangle with maybe like a super long bar and then some shorter ones? Is it possible that the one long bar could be bigger than the other bars put together if the one bar is really long? Well, here is the answer, the solution to the riddle. And the solution is that you are always better off taking 2 bars than 1 bar. There is no triangle that you can make where one side of the triangle is longer than both of the other sides put together. Isn't that cool? So there's a tip for you if you ever run into a troll guarding a bridge and he asks you this riddle. Here's what they said in the book. The sum of the lengths of any 2 sides, you can pick any sides that you want, of any triangle is always going to be greater than the length of the third side. Isn't that interesting? That's called the triangle inequality postulate. So that might get you some gold or get you to cross the bridge. But that's how it works. 2 sides are always going to be longer than 1 side if it makes a triangle. Okay? Easy peasy. Now, let's look at this triangle. This is not a right triangle, so the angles look like these are acute angles. This is an obtuse angle. So if it has one obtuse angle, then it's an obtuse triangle. Remember that? Okay, so let's look. Here, if we choose A and B, and these are bars of gold, that's always going to be bigger than C. If you choose C and A, that's always going to be bigger than B. And if you choose C or B, that's always going to be greater than A. So that's the tip. That's the triangle, what's it called? Triangle inequality postulate. Triangle inequality postulate. That's the tip, your takeaway lesson. Okay. All right. Now, what if instead of a bar of gold that made the lengths of the triangle, what if the troll had squares? Maybe he had squares like this that he could make a triangle with if he put the squares together. That now the troll is getting tricky. Are you still better off going with the 2 squares that make up the triangle, or are you better off going with the big square? Okay, it's not the same thing as just a bar of gold. Now we need more information. We do not have enough information to answer the troll appropriately. So with bars of gold, this is always true. 2 lengths are bigger than the 1 length. But if it's a square like this, in this situation, look at what we've got. We've got a long length of bar here that makes a square. And that is the 5 in that little triangle. And these are shorter lengths, and they make a square with an area of 9. If you add 9 plus 9, you get 18, and that's less than 25. So you're not better off going with the 2 squares. You're better off going with the big square in this situation. Now let's look at this situation. What if he's got one with a length of 5, another with a length of 4, and another with a length of 4? That will make a triangle right there. But here, this is 5 squared, which is 25. This one's 4 squared, which is 16. 4 squared, which is 16. You're better off going with the 2 squares of gold, because 16 plus 16 is going to be, what, 32? That's bigger than the 25. You'll get more gold if you go with the 2. But here you'll get more gold if you go with the 1. So it just depends. And what does it depend on? It actually depends on these angles. If there is an obtuse angle in there, and you have an obtuse triangle, that means with this big angle that these sides are going to be shorter, and you're better off going with the long side. Okay? Here we have all acute angles. Remember, acute means less than 90 degrees. This is an acute triangle. If you have an acute triangle, that means these lengths are going to be longer, relatively longer, and then these, you're better off going with the squares, the two squares here. So let's sum up. These are called Pythagorean inequalities. Let's sum up what we know with these Pythagorean inequalities. If it's an obtuse triangle, then the one big square is going to be bigger, greater than the two little squares. If it's an acute triangle, then the one big square is going to be less than, this time less than, the two little squares, and you're better off choosing the two little squares because that's going to be bigger. The way you can remember this is this. If it's an obese troll, obese reminds me of the word obtuse. If it's an obese troll, he's going to be stingy. The 1 bar is going to be bigger and he will only give you 1 bar. If it's an acute triangle or acute troll, she's going to be generous. She's going to give you 2. So you're better off going with the 2 bars or the 2 squares, I should say. They actually have squares. I shouldn't have put bars. I should have made squares. Let me fix that. Yeah, they should have squares of gold. So the obese troll is only going to give you 1. The cute troll is going to give you 2 squares. Those are bigger. Okay. They're both going to actually give you the bigger one. The obese troll is just going to give you 1 square instead of 2. Let's do an example here. Let's see how might people make this into a math problem that you can do. All right, here's what the problem is. The lengths of the sides of a triangle are 7, 5, and 4. Is the triangle a right triangle? Is it an acute triangle? Or is it an obtuse triangle? Okay, so that's interesting. Let's just draw a triangle. Any triangle. Whatever, we'll just draw a triangle. Okay, I like how it fixes it for me. The lengths of the sides are 7, 5, and 4. I'm going to put 7 right here because that's the largest side it looks like. I'm going to put the 5 here and the 4 here, but it doesn't matter. I'm just using this to help me sort of visualize it. Is the triangle a right triangle, an acute triangle, or an obtuse triangle? So we need to compare c squared, and then we need to compare that to a squared plus b squared. If it's equal, then we know that's the Pythagorean theorem, so that must be a right triangle. Okay. If it's not equal, it's going to be one of two things. The c might be greater than, that's only 1 big square of gold, so that would be an obese troll or an obtuse triangle. Okay? If the c is less than a squared plus b squared, that means the a squared plus b squared is going to be the bigger thing, and that's a cute troll that's giving you that, or an acute triangle. So we just need to figure out what's bigger, a squared plus b squared or c squared, or is it the same? C is always the biggest side, so that's 7. 7 squared is 49. Okay, what about a squared plus b squared? And it doesn't matter here which number you choose for the a and which number you choose for the b. So it's going to be 5 squared plus 4 squared. 5 squared, 5 times 5 is 25. 4 times 4 is 16. So 25 plus 16, 41. 49 is bigger, so the c squared is bigger. So we know that it's not equal, so it's not a right triangle. We know that right away. Now we just need to decide, is it an acute triangle or is it an obtuse triangle? And since the c squared is bigger, I'm going to go with obtuse or an obese troll. All right, let's go on to the next section. The next section is polygons. Polygons have certain qualities about them. They are simple, they are closed, that means it's not an open shape like that where it doesn't match up. They are coplanar, meaning they're all on the same plane. You can draw them on a two-dimensional piece of paper. It's not a 3D thing. The sides are all straight lines, so if it's a curvy line, that's not a polygon. They're geometric figures and they don't cross themselves. So if you have something like that, that is not a polygon. That's something that Nora draws. All right, so let's look at some examples. I'm going to put the donkey here because all of these are not polygons. So let's go through and say why they are not. Well, this one crosses itself, so that's not a polygon. This one also crosses itself, so no. This one has a curvy line right here. Curvy lines are not allowed in polygons, so that's a no. And this one has an open space right there. It has to be closed. These are all actually polygons. So Dwight is right when he is looking at these and wondering whether they're polygons or not. He's saying, yeah, it's true. These are all polygons. Why are they polygons? Well, each figure they're simple. They don't have curvy lines. They're closed. They meet all the criteria. This polygon has an indentation. That is totally allowed, and that is called a cave. I sort of imagine that like as if we're speaking Spanish. Con meaning with, concave. That means it is with cave. So with a cave. So imagine like a Spanish word, concave. If it's concave, that means it has a cave in it. If it doesn't have a cave, then it's a convex polygon. So these would all be convex, and that means no cave. And if you're not sure, if you look at something and you're like, I am not sure if that has a cave or not, use the dot game to see if it's convex or concave. The dot game is like kind of the most boring game in the world. But if there are two dots anywhere inside the cave that cannot be connected by a line that stays inside the shape, that's concave. If you stay inside the shape, that's convex. If it crosses the shape or goes outside of the shape, that's concave. Now, we said we were going to talk about similar polygons. What does that mean for polygons to be similar? Two polygons are considered similar if one is just like a zoomed in version of the other or a zoomed out version of the other. So they're similar if it's just a magnification or a reduction. It's still going to be the same shape, the same angles. If it's zoomed in or zoomed out, they're similar. So let's look at these polygons and try and decide if they are similar. And it turns out that they are. They have the same shape. And if you took this one to like a copy machine and magnified it by 1.4, it would be this shape. Okay, so even though these lengths are not the same, they're proportional. The lengths are proportional. So that's the thing that is important. What does that mean that it's proportional? That means this purple side here is the same as this purple shape. They correspond to each other. So if I'm going from big to small, then it's 5.6 corresponds to 4. And if I do the math there, 1.4. What about, now they all have to be proportional if they're similar. So let's look at another side. How about the pink side? 4.2 is to 3 in the same way that 5.6 is to 4. So if I do the math there, 4.2 divided by 3, I have to get 1.4. And that would be true of all of them. 2.8 over 2 is the same as 1.4. 7 over 5 is the same as 1.4. Sometimes the way I think about it is I do, instead of figuring out the scalar factor, because that's what we're figuring out here, this number is called the scalar factor. That means how much do you magnify it when you go from left to right? The scalar factor from left to right here is 1.4. And if you're going from right to left, the scalar factor is 1 over 1.4. So if you know one of the sides on the right is 5.6, if you multiply it by 1 over 1.4, you should get what the side is on the left-hand side if you're going from big to small. Okay, so that's how you use the scalar factor to figure out the sides. I actually like to do it a different way. I kind of like to use corresponding sides and do ratios. Let me show you how to do that really quick. So this side is the same as this side, and this is the same as this. Okay, so I can make a ratio. 5 is to 7 as 4 is to 5.6. When I multiply this out, like cross multiply, you should get something that is equal. So 5 times 5.6 is equal to 7 times 4. That means 28 is equal to 28. Yeah, cool, right? So that's how you know that it's proportional if the ratios are equal like that. Okay, let's make sure that you know a couple more vocabulary words. The vocabulary words are vertices. The vertices are the pointy angles right there. So that's a vertex or vertices for more than one. The sides obviously refer to those sides. the length of that. This right here is a polygon, and this actually is a similar polygon, even though it looks a little different. All we did is we took this polygon, I actually did this to make this, and I flipped it and I put it over there. Okay, and I shrunk it a little bit. So I know that all of the angles are similar, even though the lengths of sides are going to measure differently because I shrunk it. The angles are all similar. But you have to make sure that you've got the right angles. So for example, angle A is the same as angle P. Angle B is going to be the same as angle Q. So be careful when you're doing your ratios that you're actually comparing similar walls when it's flipped around like that. Now, is it possible to have angles that are the same, but the lengths are not the same? It is possible. Look at this. Look at these rectangles right here. This rectangle on the left has lengths of sides that are 3 and 4, but all of the angles are the same. They're all 90 degrees. But you could have a square over here where all the angles are still 90 degrees, but the lengths are 2. So these are not similar because the angles have to be proportional, but also the sides have to be proportional. There's one unique polygon that we should consider that is really special, and that is a triangle. Triangles are special because if the angles are proportional, automatically all the sides are proportional. You cannot draw a triangle with exactly the same angles unless they're proportional. It's always, the lengths of sides will always be proportional. So because of that, the math nerds have decided, well, we don't want to be redundant and say that the angles and the sides have to be proportional. If we're talking about triangles, similar triangles have corresponding angles that have equal measures, and they don't mention anything about sides. So as long as the angles are proportional between two triangles, you know automatically that it's going to be similar triangles because the sides are also going to be proportional because triangles are what? Special. Yes, they are. Let's look at an example here. We have this triangle on the left with a 30-degree angle and a 130-degree angle. And on the right, we made a bigger triangle with a 30-degree angle and a 130-degree angle. Now, the special thing about triangles is that all of their angles have to add up to what number? They have to add up to 180 degrees every single time, right? So if we add these up, 130 plus 30, we get 160. We know automatically this other angle is going to be 20 degrees, and it's going to be 20 there. So that means all of the angles are proportional. All of the sides have to be proportional. This is going to be the same as this side over here. Not the same length, but proportional. Okay? Now that we know that if all you have to have are two angles that are similar, and then the whole triangles, they're going to be similar. That's so cool, isn't it? That's so cool. All right, let's do example 3.2. I love these problems because they're just so fun and satisfying. They want us to find x and find y. And you can't just say, I found it, it's right there. Now these triangles are similar. How do we know that they're similar? Because the tick marks are telling us that these angles are the same. And the tick marks with 2 are telling us that these angles are the same. So which walls are going to be similar? I want you to focus on this first because this can be really tricky. This wall right here, or this length, is between the angle with the tick mark of 1 and the angle with the tick mark of 2. You might think that it's this one, but it's not, because this corresponding triangle has this length that is between angle 1 and between angle 2. And so that side actually goes with this side. It's like the triangle is also flipped. It's right? They flipped it and turned it or whatever. Always do this first. Like make sure that you're getting, this is the only way you can get these problems wrong because they're easy, but your friends are going to get them wrong because they're not going to do this, right? So the purple walls are the same. So this X and this 6, those are similar. All right, so let's find the x first because this is going to be easy. So what we have to do is, let's do it my way with the ratio way. Let's put, let's make a ratio starting with the small triangle on the left, 5. And that is compared to the same wall on the right. If we compare it to the same wall on the right, that's going to be a 7. So 5 is to 7 as x is to 6. Does that make sense? We're using the same corresponding wall. 5 is to 7 as x is to 6. Now we just need to cross multiply and find the x. It's so easy. I love it. I love it. I could do these problems all day long. Let's do it. Cross multiply. So 7x is equal to 5 times 6, which is 30. X is equal to 30 over 7. Okay, so I'm going to write that there, 30 over 7. All right, that's cool, but now we need to find the value of y. Y is the same as this 4 over here, so let's use that. You could do any ratio. You could start on the other side, on the other triangle if you want to. So we could say y is to 4. You just have to put the same one on top. If it's the y on top, you have to pick another number on the right-hand triangle that's on top. Y is to 4 as 6 is to, ooh, I almost messed up, as 6 is to x. You could do that. Yeah, absolutely. Or you could do 7 is to 5. I'll do 7 is to 5 because we got, like they gave us those numbers, and so I know that those numbers are right. Do you get how I did that? Y is to 4 as 7 is to 5. 7 times 4 is 28 is equal to 5 times y. Just divide by 5, and you've got y is equal to 28 over 5. There you go. We found x, we found y. Oh, math, I have missed you. Do you feel like Lisa does right now as you're doing these problems? These are so fun. I love them. Okay, the other thing that you could do is find the scalar factor. On this problem, they want us to find x and y and z. They don't tell us which angles are similar, except they put a right angle here. So I know that those are similar. And I know that since these sort of cross each other like that, those are transverse lines, that those angles must be similar. So I'm going to put a little mark there. And then I know that these angles must be similar because if two angles are the same, then the third angle has to be the same. Let's mark which walls are the same. If you don't have colored pencils, you can do it with tick marks or the way you circle or underline or something. 10 is between the small angle and the orange angle. So I'm going to make that greenish color. 7 is between the small angle and the orange angle. So I'm going to make that the same color. I'm going to use red for the length between the right angle and the pink one. Right angle and pink one on this side is that. How about purple for that last side? Now I know everything that is corresponding. As I'm looking at this, I see two unknowns, x and z. So that one's a little tricky. Let's find the y first, because the y goes with the 8, and that one is a known number. So I'm going to say y is to 8 as, now I started on the left-hand side, so I have to pick a number over on the left. I'm going to pick this 7 and 10. Y is to 8 as 7 is to 10. Cross multiply. 8 times 7 is 56 is equal to 10y. Divide both sides by 10. Y is equal to 5.6. That was fun. But how in the heck do we solve the rest of the problem? Because you can't compare these using ratios because they're two unknowns of the same wall. But they give us another piece of information that is a clue, and that's this angle, the right angle. Whenever you have a right angle, you can use the Pythagorean theorem. A squared plus b squared equals c squared. So let's look at this triangle on the right. This is going to be A, this is going to be B, this is going to be C. It doesn't matter which one's A and B, it just matters that C is the longest one. You could have used the Pythagorean theorem for this side too, now that we know this value for y. So using the numbers on the right, 8 squared plus z squared equals 10 squared. It is 64 plus z squared equals 100. I'm just going to keep going over here and subtract 64 from both sides, so I end up with z squared is equal to 36. Square root both sides. Z is equal to 6. Now you totally have a choice, whatever you want, whichever method you want to use to find the x. You can just use the ratio method, or you can do a squared plus b squared equals c squared again on that side. I like the ratio method, so I'm going to stick with that. I'm going to say 7 is to 10 as x is to 6. And then I cross multiply. 10x is equal to 42. Divide both sides by 10. X is equal to 4.2. Bam, we did it. We found x, 4.2. We found y, 5.6. We found z, it's 6. You having fun yet? Hey, we are all going to have fun here. Let's do another example because we're having so much fun. They want us to find the lengths of A, the lengths of B, the lengths of C. This is tricky because A is just this length of this small triangle, and B is just this part of what is a bigger triangle. And C is the long part of a big triangle. So it's the same thing as we've been doing, it's just they drew it overlapping and they're being a little tricky by just only referring to that section. That is all they're doing. Otherwise, it is the same exact thing. We're actually going to be comparing this triangle with this triangle. What is going to be easiest to go for first? We know 2 out of 3 of those sides. And we know this side of the big one. I think it's going to be easiest to go for C first. I think these are going to be a little trickier because they're split up. So I'm going to say 6 is to 10. Do you get why I did 10? When I compare those two triangles, those sides are the same. These are the same. This one is proportional to that one. So 6 is to 10. Don't just do 4, you got to do the 10. As 4 is to C. You got to get the ratios right or else you'll get the wrong answer. Cross multiply. 40 equals 6C. C is equal to 40 divided by 6, which is 20 over 3. So we've got the first answer. Now I think it might be easiest to get A plus B next, because we know this side and we know this side of the big triangle, and we know this side and we know this side of the small triangle. But we can't do ratios because these are both unknown on the small and the big triangle. But these are right triangles, so we can use the Pythagorean theorem. Let's do that. I'm only looking at the big triangle now. What's A? It's going to be 10. B is 20 over 3. We just figured that out. What's C? C is this entire length. C is equal to A plus B. Okay, 10 squared is 100. 400 over 9. I used my calculator and got C is equal to 12. So this whole thing is 12. I just noticed another thing that we could have done that would have been easier too. Check this out. We know this side of the small triangle. We know this side of the small triangle. So we can figure out A using the Pythagorean theorem. So let's do that, but only looking at the small triangle. A squared is going to be 6 squared. B squared is going to be 4 squared. And that's going to be equal to C squared, which is actually A squared. It gets confusing when the letters are the same as the Pythagorean theorem. 6 times 6 is 36. 4 times 4 is 16. That equals 52, which is C squared. C is going to be the square root of 52, which is equal to 7.2. Okay, so now we know that this length right here is 7.2. We already figured out that A plus B is 12, so actually all we have to do to figure out B is do 12 minus 7.2. and that turns out to be 4.8. So we found A, B, and C. We did it a little bit differently than the book, so you can look at the book if you want another way to do it. But we're having fun, right? I could do this all day. I'm so sad this is the last example. They want us to find A, B, and H. And there are lots of triangles here. There's this triangle, there's this triangle, and there's this big triangle. Okay, apparently this example is unique and famous because there are actually 3 similar triangles. It doesn't look at first like any of them are similar because you've got this angle with 1 tick mark, this angle with 2 tick marks, but the way it's drawn, this tick mark goes with the small triangle, but it also goes with this other big triangle because it's the same angle. So the only way that I can do this is I have to draw these triangles again and draw them separately. The length of this long side is 8 plus 4. So when I draw it over here, I'm just going to write 12. Now I'm going to draw this small triangle. Now I'm going to draw this last triangle. Added a 90-degree angle here because if this one's 90 then and this is a straight line, this also has to be 90. All right, check it out. Remember how we said if 2 angles are similar, then the third one has to be similar? This has angle 1, the right angle, angle 2, the 1 tick mark. So that means this has to have the 2 tick marks. I don't know what that angle is, but I know it's similar. Same situation over here. If you've got the angle with 2 tick marks, you've got to have the angle with 1. Now we just have to make sure that we get the ratios right. Great. Let's do a little bit of highlighting. This line B is between the right angle and the 2 tick marks. Right angle and 2 tick marks. Right angle and 2 tick marks. See, you would never know that those were the corresponding sides unless you connected the angles. This line is between the right angle and the 1 tick mark. Right angle, 1 tick mark. Right angle, 1 tick mark. This one's the hypotenuse. Hypotenuse. That one's also always going to be c squared. Now I'm going to scan through. Do we know 2 of these sides on any of the triangles so I can use the Pythagorean theorem, a squared plus b squared equals c squared? No, we don't. So we're going to have to use ratios, which is fine. I love using ratios. So fun. Now when we use ratios, I have to have most of the ratios where we know the numbers, but we only know 1 number from 2 triangles. Like if I choose to compare this triangle with this triangle, I'm going to say A is to 12 because those are corresponding sides. Ooh, check this out. I can do A is to 12 as 4 is to A. Those sides are both blue. A is to 12 as 4 is to A. Will that work? Let's try it. Then when I cross multiply, I get 36 is equal to A squared. A is 6. Sweet. Put a 6 there, put a 6 there. Sweet. That was a ton of information we just got. Super satisfying. What should we find next? Let's find B. Let's compare this triangle with this one way over here. Why not? Let's do the same thing. Let's compare the green sides. B is to 8, and let's compare that with the purple sides, as 12 is to B. Times 12, 72, is equal to B squared. B is equal to the square root of 72, which is a huge decimal, so I'm just going to leave it like that. Now all we need to do is find H. Since we already used ratios, this time let's use the Pythagorean theorem. You can use any of these triangles because they're all right triangles to use the Pythagorean theorem. Let's do it with the easiest one, which is this one. The other ones have square root 72, so I'm going to choose the easiest. So 4 squared plus h squared equals 6 squared. 16 plus h squared equals 36. What's 36 minus 16? H squared equals 20. H equals the square root of 20. That's really all you need to put. Well, you could say 20 is 4 times 5. The square root of 4 is 2, so you could simplify it to 2 times the square root of 5. So I'm going to write that in place of h. Sweet! That was our last problem. But you can do the homework. Believe in yourself and you can do it. Have fun with the homework. Bye.